Okay, so we are going to start lecture number 21. It's this, I'm going to repeat, of course 21 is 19, that's the same slide. That this is the schedule for your presentations. So from next week, for the next 2 weeks, you'll be presenting. April 21 is actually April 19, so you know that is the typo error in the slide. For the term paper presentations, you need to upload your presentation before the class on this classroom PC, and you can bring the pointer, or you can ask it if you need it while explaining your presentation. Maybe Dr. Wall has it, but if you have your own, that's better. So you'll be using the classroom computer, and what happens that if you have, there are 3 presentations or 4 presentations, so before the class starts, all of you put your presentations on the computer. So that after that, in sequential process, that can continue. Okay, there is an homework, simple 3 questions. Homework number 6, 2 questions from the book, page number 40 to 42, 2.1 and 2.4. And the third question, that is, what is the effect of hydrogen adding and oxygen adding on silicon and silicon dioxide? Okay, so I just want to see that whether you have understood or not. I'll upload these slides, so if you don't have that homework, you can see. Otherwise, you can note it down. Okay, so we stopped at this point last time due to that siren. That is, we were talking about anisotropic etching. Okay. So, as I told you guys that in dry etching there are 2 mechanisms basically. That is, one thing, to make it reactional, we have the ionic bombardment, and secondly, there is a chemical reaction. Those ions are very selective towards the surface, though if even they are low energy ions, they can react with the surface and they can make it volatile and get away. So reactive ion etching is actually the combination of these 2. That's why we call it as reactive ion. So these are ions, at the same time they are reactive to the surface. So that's why on the right hand side you can see that we have very directional. If the ionic species are reactive with the surface, in that case the Etch rate would be high, and if you are bombarding it, in that case you will be getting the high aspect ratio. So we make it directional as well as selective, because if they are not reactive to the surface, it means they are not selective to the film. Because if they are no more reactive, it means that just due to the physical sputtering you are etching with the surface, so it will damage the substrate, it will damage the mask, photoresist or anything, the same way as it damages the film. So that's why it's always, in order to achieve the selectivity, you always go for reactive species. This graph may tell you, you can see that both mechanisms are supported by plenty of experiment evidence, which shows that dry etching is most enhanced by the combination of both the mechanisms. One thing is chemical reaction as well as ionic bombardment. So reactive ion etching is also a combination of that 2, I told you. And that graph on the left hand side, you can clearly see that if you have initially, the experiment shows that initially you supplied only gas, that there was no ionic bombardment. So when the gas was not energetic, when it was not actually bombarded at the surface, in that case the etch rate was very slow. In the middle, you can see that reactive gas has been combined with the directional bombardment of those ions. So the etch rate increases very high. In the last, beam only. So in the beam only portion, actually you are only bombarding the ions, but that gas ions are not selective to the surface. If they are not selective, you are just physically sputtering it. So it means the etch rate would be slow. So it clearly, the experimenters will clearly show that the combination of the 2 actually gives you a high etch rate, and that makes sense too. Okay, so in the etch process, we have talked all of these things. That first of all, it should be selective. If X is actually the substrate, Y is the film that needs to be etched, and Z on that graph, on that figure, Z is actually the photoresist mask or any other mask it may be. So selectivity with respect to X, Y and Z, that we call it as film to mask ratio. Film to mask H ratio, so means that how selective it is to the film with respect to the mask. So that's why you should know that what is the selectivity between Y, Z and X. Secondly, H rate, that how fastly it etches in the vertical direction and in the lateral direction. That is named as lateral H ratio. So that is also the second thing that you should know before deciding about the etchant, because I want to make it directional. If it etches 100 angstroms in the vertical direction, how much I etch my side walls? What is this lateral etching rate? So you should know about that lateral H ratio too. And thirdly, that because I told you that it's perfectly, you don't get anisotropic etching. It's always there is some certain angle that the side walls actually form. So you should know what is the angle. Ideally, we want it 90 degree, but it's not always 90. So you need to know what is the theta, what is the anisotropy. Okay, so that is actually the angle of the side walls that they form with the substrate. So these are the three things that you actually, three requirements that you need to know before selecting any etchant for the dry etch process. This slide also talks about the same thing, that the parameters that can change your etch rate and that are actually important for the etchant selectivity. First thing, what is the etch rate? Of course, that is one of the important things. Bias, that what is the voltage potential difference you apply. You know that in order to have the bombardment, the wafer is always at cathode, that is the negative potential, and that's why the plasma ions, they move towards the negative plate, that is actually, they are actually bombarding on the substrate. So what is the potential that you are supplying between the two? What is the selectivity? What is the loading effect? I know that you may not, we have not discussed up till now the loading effect, but I'll discuss the loading effect in the next slides. Profile effects, that is what is the anisotropic ratio, or if there are any micro trenching, we will discuss the micro trenching as well in the next slides. So these are the few things that you already know, except the loading effect. I'll let you know what is the loading effect. But loading effect is also important in etching. Okay, so this slide talks about that surface micromachining and bulk micromachining. You know, these are two different things. When you're dealing with thin layers, when you're patterning the thin layers, that is actually named as the surface micromachining. And if you're etching away the whole bulk of substrate, silicon wafer or any other thing, so that is actually the bulk micromachining. So especially in MEMS devices, or when you have couple of layers, or when you want to design, for example, cantilever or some other device, so in that case you need to deal with the surface micromachining. The parameters are the same, but it's just you're working at smaller dimensions, that is the thin layer, so the thickness of the film that you are actually etching, that also matters. So there are certain parameters that you need to keep in mind while dealing with the surface micromachining. Reactive ion etching, that can increase the aspect ratio. Now I expect you guys to know what is the aspect ratio. It is actually the vertical etch rate and divided by the actually the vertical dimension divided by the critical dimension, or I would say the horizontal dimension, that what is the minimum feature size. So that is the aspect ratio. It's not vertical etch rate divided by lateral etch rate, that is actually the lateral etch ratio. So aspect ratio is different from the lateral etch ratio. So you can see that, in other words, I would say the deeper the trenches, the higher the aspect ratio. So this distance divided by this distance. So it's actually the ratio of two lengths. The aspect ratio is always in this much micron divided by this much micron. So high aspect ratio can be achieved by reactive ion etching, just we read in the last slide. How you achieve high aspect ratio? As I told you that in dry etching, by making it directional, by bombarding the surface, you achieve the high aspect ratio. So in the chamber you have low pressure. Due to that low pressure, the ions can move freely. The mean free path of the ions that actually increases, you know this thing. After that, you can increase that rate, or one thing that while achieving high aspect ratio, as I told you, that because you are bombarding the surface, so the mask or the substrate that is also damaged due to that bombardment. But higher the selectivity of that species with respect to the film, the lower would be that damage. And similarly, for how much time you are doing that, whether you are over etching or not over etching. So if you are over etching the surface, we will discuss what is over etch. In that case, the damage would be higher. Okay, deep reactive ion etching, DRI, will discuss in, maybe last time I talked a little bit about DRI. Did I? When I said that there is some passivation layers, so in DRI I would do this thing that there are cycles of passivation layer and etching, passivation layer and etching. Okay, so we will discuss today deep reactive ion etching is actually to achieve even higher aspect ratio. When you have very deep trenches, you want to etch that, then you go for deep reactive ion etching.
So I have questions previous slide. How we can control mean free path of the ion?
How can we control?
How to increase that? How to increase? We need to increase mean free path of ion to get high aspect ratio. So how we can increase? How one method we use?
How we can decrease or increase?
I mean generally control.
The mean free path. This is what you're saying. Okay, actually, when you introduce the plasma, actually the plasma, they are energetic ions. So higher the energy, higher would be the mean free path. And similarly, by the chamber pressure, the mean free path is also affected by that. So if you change the chamber pressure, the mean free path, that would, because the mean free path is actually depending upon two things. One thing, what is the energy of those ions? Secondly, how the environment is. If the environment is putting up some pressure, of course they cannot move freely. If the environment they are not experiencing some external force, so they can move freely. So these are the two things. What is the energy? By increasing the energy, you can supply high plasma, so higher energy, or you can decrease the chamber pressure. So these are the two things that you can control.
I mean, is it predefined that for this energy we can, my mean free path will be like this amount?
Yeah, actually, if you're talking with respect to etching process, in etching process, you don't need to. You don't need to know about what is the mean free path of this etching that I am using. So these are not the parameters that you actually consider when you're finding out what is the etch rate. These are actually at the lower in the background what is going on. I mean, just to make you people understand. While etching with the equipment, you need to just know, okay, what should be the voltage that I should supply? What should be the pressure that I should supply? So you define the recipe based upon those. You know that by increasing the pressure, your etch rate increases. So, but in the background, by increasing the pressure, actually what you are doing, that's you are supplying more number of etches we have introduced. It means that the mean free path may be affected. There is a trade-off that will be decreasing. So they are at the background. These are the things that just to make you people an understanding that why the increase or decrease of pressure actually affects my etch rate. But while working on the equipment, you don't need to worry about what is the mean free path of the etching that I'm using. So you don't go into that much detail. This is just for the discussion purpose. But of course, if you are going to design, if you are going to, when you write paper and you make some assumption, then you need to discuss at this physics level. Then you get into the deeper level that I am experiencing this thing, and I think because every paper, every research paper is actually based upon some hypothesis or assumptions. There are some certain assumptions. So you talk about this thing that I am assuming this because then you go into the physics of that thing, and by using the physics laws, you try to prove your hypothesis. Okay, so as I told you, deep reactive ion etching, high density plasma. High density plasma, I talked about 3 types of coupling last time: capacitive coupling and inductive coupling. I told you that inductive coupling is used to produce high density, and capacitive coupling is not used to produce that much high. It's usually low density or even medium density is okay. So it's high density plasma. It means it is, if somebody asks what is the mode of power you are generating here, so that would be inductively coupled power source. Cycles of etching and polymer deposition. So as I told you that there, maybe the next slide will explain it better. Yeah, this slide. So I said that there will be cycles of deposition, the polymer deposition, and etching. Then deposition, that is the passivation layer actually. That polymer deposition acts as a passivation layer. So you can see that in the first step there is an isotropic etching. Okay. After that, in the second cycle, we actually deposit the passivation layer, and that passivation layer is removed only from the bottom instead of from the side walls in the third step. And again, in the last step, we again do etching. So etching, passivation layer. After this etching, we'll again deposit the passivation layer. So the bottom line says that the cycle is switched to the passivation layer before the passivation thin film on the side wall disappears. So this is how you actually multiplex that. What should be the elapsed time between the passivation layer cycle and the etching cycle. That you need to make sure that the etching cycle should stop before the sidewall passivation layer is disappeared. You again go to the passivation layer. So again, you remove the passivation layer from the bottom and you start etching. When you start etching, due to the isotropic etching, here actually I would say this thing should not appear. Okay, because in the next passivation layer this should appear again. So this thing goes away with this etching because this is isotropic etching. Again, you do the passivation layer and remove from the bottom. So meanwhile it etches from the bottom. Meanwhile the sidewall passivation layer also goes away. So before that sidewall film goes away, you need to switch to the passivation layer cycle again. So this is what we are discussing here. That cycles of etching and polymer deposition, they are used for deep reactive ion etching. Photoresist selectivity, that is 100:1. So that is very good selectivity. That the photoresist is 100 times inhibitor as compared to the film. Oxide selectivity is even more, 200:1. So it means that oxide would be better masked as compared to photoresist. If you want to have very high aspect ratio etching or something. Cryogenic dry etching. So cryogenic gases always used to generate very low temperature. As you know, maybe half of your class who were having the lab yesterday. So we use the cryogenic gases to generate that low temperature. From the lab, I just remember that because yesterday we could not do that, but they have fixed it. There was some wire that was broken down. Yeah, so that's why the voltage was not turning on. So the system is up again, so we can use it tomorrow. How many of you can be available tomorrow? Because 9 to hopefully 12 will be done with the first group. So I expect the second group to come by 12. It should not take more than 1 hour. It should take less than 1 hour, I believe. Because you know that when the cryogenic pump is already less than 18K, in that case it takes only 5 minutes for the rough vacuum. Those who were present yesterday, they are understanding what I'm talking about. So it should not take more than maybe half an hour to 45 minutes, I would say. So anybody who has class at 12? Nobody? Okay, so in that case I'll send you an email today 9 to 11. So hopefully we'll be done by 11:30 or 12 by the first group. So it's better if you come at 11:30 so that we can at least load the sample simultaneously and we can do it in parallel. Okay, otherwise 12 is fine too. So I'll send you guys an email so that we can complete it tomorrow. Otherwise, we can switch it to the next week, but in that case, it will delay the lab 1 week later. So I don't want you guys to work on the lab part in your final exam week. So I want to get it finished by the 25th of April, so that the last week even of this month, that would be free for you guys for focusing on the other courses or even the classwork. Because I know for this course, you have key paper review, maybe you will be having group research proposal too. Are you going to have this in this course or no? Okay, so usually Dr. Iqbal offers that too. So, I mean, you are busy with other stuff too. So, we'll be doing the deposition of aluminum tomorrow on all the 12 wafers. But you cannot load all of them all together, so we'll be doing that in 2 steps. Okay. Etch uniformity. You know this thing that when we were discussing about the etchant, that what should be the properties of an etchant while selecting that whether this etchant is good or no, out of many parameters, like it should be having high etch rate, it should not be very dangerous, it should be readily available, there should be some way to dispose that etchant, all of other parameters. There was one thing, that is the uniform etch rate, wafer to wafer, batch to batch, or die to die. Remember, this was also one of the things, that an etchant, a good etchant, has these properties. Out of those properties, the uniform etch rate from wafer to wafer or batch to batch level, that was also one of the properties. So every etchant should have the uniform etch rate. So how you define the uniformity? That is actually the difference difference of the etched film at different spots over the wafer. So if you talk about the etch rate percentage uniformity, that would be the maximum etch rate minus the minimum etch rate. That is the difference of the etch rate, maximum minus minimum, divided by maximum etch rate plus the minimum etch rate multiplied by 100. So this is how you calculate that what is the percentage of uniformity of etch rate that you can achieve. So the uniformity of the etch rate means that that etchant should etch the same way on all the surface of a single wafer, or on all the surface of all the wafers if we talk about at batch to batch level. Etch selectivity, the second thing, that the etchant should be very selective as well. So how much it is selective with respect to the mask, that is we termed it as film to mask etch ratio. If you remember, I told you that how you practically actually do that you calculate what is C, what is D, and C by D is actually the film to mask etch ratio. So that's how you calculate that. And whenever you decide that, okay, this is the etchant for this process, you always need to know how much it is selective with respect to the other photoresist. And it's not only the photoresist, whatever the materials you have on that substrate. If you have, sometimes it happens that I know that this gas can be used as an etchant for this material, but for my application I cannot use that gas, because in my application I have some other material that you don't have in your application. I have that material, and that is not selective with respect to my film to that etchant, so I cannot use that etchant. So you always need to know that what is the etch selectivity of your film with respect to all the other materials. It may be the etch mask, it may be the substrate, it may be the other material, that what is the etch selectivity. So we always want that the etchant should only be attacking on the desired film. It should not disturb the undesired or unwanted film etching. So these graphs can show you. The first graph, it shows that it's very isotropic, but it's highly selective. Can you see that? The first graph, the first figure. In this case, it's isotropic, but it's very selective. How I can see it's very selective? That it did not etch my photoresist at all. It did not affect my photoresist. So I would say, as you can see, ideally selectivity. Ideal selectivity means that ideally I would say that it did not even affect my photoresist and it etched away all this film. But that's ideal. Usually it does not happen. It may be 100:1, maybe 200:1, as we saw in the previous slide. So even more than 10:1, that is good for selectivity if you don't have a very thick film to be etched. If you have very thick film, if you have a film that is more than 10 times thicker as compared to my mask, so 10:1 would not work for that, because if I need to etch my film, at the same time my photoresist has gone away. So that's why this is ideal selectivity. If you see in the second figure, you can see that it's not very selective. It's not very selective because my photoresist has also been etched away with the film. At the same time, it's not selective with respect to photoresist, and it's not selective with respect to the substrate. So you can see by over-etching, my substrate has also been etched away. This is the substrate. So substrate has also been etched away, means it was not selective towards my substrate as well. So you cannot go for the over-etching. In most processes, when you need to remove certain film absolutely at all, you always go for over-etching process. So if I know that this much is the thickness of the film, this is my etch rate. So based upon those two things, you calculate what should be the time to remove all that film thickness. So I will always go for over etching, maybe 30 seconds extra, maybe 1 minute extra, depending on what is the etch rate. So that make sure that there is no residual of the film that is left there. But in that case, I always consider my substrate as the etch stop. That it's very selective towards the etchant, it should not etch away. In this case, the over etching process cannot be done if you don't want to etch your substrate, because that etchant is not selective with respect to the photoresist, is not selective with respect to the substrate. In polymers process, if you know about the polymers, that is always over etching process.
So I have one question. So if we etch away the substrate, that thing can be a problem for like device later.
Of course, it depends upon your application. If in the design I have not I don't want my substrate to be etched away, so in that case that can create problem for my device. So it depends upon your application. In some application, maybe it's not affected, but at least the point is that it's not giving you what you want. It's not it's actually at this point I will say that it's actually distorting my substrate as well, that it's unwanted or undesirable etching that I don't need actually. But if you need it, then of course you can use some method. But usually we always use an etchant that is selective to a certain film. If you have two films, you always go for two separate etchants. If in certain application I want to etch that, let's suppose I want to etch my substrate. So I will use one etchant to remove that film, I'll use another etchant to remove that substrate. Because that is always selective with respect to, because as I told you, that selectivity is not ideal. Similarly, the lateral etch ratio is not ideal. You don't always get 90-degree angle. There will always be some lateral etch rate as well. Your side walls would be affected. So if it's very selective, you can have more directional. You can have less effect on your side walls. What I'm trying to say that if the etchant that I'm using is very selective, it won't affect my this film on the side walls if I don't want it. So that's why I would prefer to use an etchant that is only selective to my substrate if I need to etch it. Okay, if it's not selective, these side walls would also be somehow to a certain extent they would also be etched. Okay, so this slide talks about the over etching process, that in certain cases why we go for the over etching process. You can see in the figure that if you have the directional etching, and in this part just with the film the thickness is high. Okay, so if I had the directional etching, I know the etch rate, I have decided this is the time that I should etch it for. So in that case there would be some residue of the film that needs to be removed. It's actually like this, that if there was a residue and after that I deposited the second film, this was the first film, so you can see that in this part the thickness is the same as in this part. So if I have exposed my wafer in dry etching or even in wet chemical etching, but because it's directional, so I'll assume it as dry etching. So if I have exposed by measuring the thickness of film 2, in that case, in this case, this much thickness will be moved, but this is left. So that's why I always prefer to go for over etching, so that I make sure that there is no residue left. So this slide just shows that over etching, why over etching is needed in certain cases, or why over etching we do, because due to the topography of the underlying surface, maybe at some points the thickness is different. So the uniformity of the thickness of the film over the wafer, that also counts towards the uniformity of your etch rate. Maybe at certain point the thickness was not the same as at the other point on the wafer. So it will actually ultimately conclude towards the etch rate non-uniformity over the surface. So they are interrelated actually. Okay, so to completely clear the film and over etch, typically 15 to 70% of main etch time must be applied. So we have discussed this thing, that the over etching is needed in certain cases. Why we need the over etching? That is the cross wafer etch rate and film thickness uniformity. So as I told you that the film thickness is non-uniform over the surface. As we see in this previous slide, if the film thickness is non-uniform, it means that at certain points where the film was thicker than the other points, there would be some residue of that film. So in order to compensate for that non-uniformity of the film thickness, we look for over etching process. We always go for over etching process. Similarly, as this film thickness can vary due to the non-uniformity of the film thickness, similarly the etch rate may also be different. Maybe in some points where you have trenches, or where you have the critical dimension area or the minimum feature size area in that part, because if I'm talking about the wet etching or even in the dry etching, that the etchant cannot be as effective and efficient in that part as compared to the other part. So it means the etch rate has decreased in that part. So etch rate itself is not uniform all over the wafer surface due to that pattern or the topography that we have. So in order to compensate the cross wafer etch rate, non-uniformity of the cross wafer etch rate, we need the over etching. So over etching compensates both the non-uniformity of the thickness and the non-uniformity of the etch rate of the wafer. And locally thick regions over underlying film topography, as I discussed in the last slide, that the underlying topography, if there is some residue, the next film actually makes it thicker in certain parts. So locally there is some non-uniformity of the film that arises due to the underlying topography. As those who are taking the advanced films, they know that the topography, the underlying topography, it actually is affected in the next deposition processes. So if like this, if I want to deposit 200 nanometer of oxide, so in this part it will be at this level, but at this part it would be at this level because it's 200 nanometer over here. So if I'm considering this is my underlying topography, so it's going to affect my thickness as well. So if there is some, I'm considering if there is some residue here, this much. So in this part, 200 more, so there will be 400. So underlying topography can affect it, as we saw in the previous slide. So all these non-uniformities are actually undertaken by using the over-etch process. Okay, now this slide talks about that the cross-wafer uniformity and selectivity of an etch rate are closely linked, as we discussed before. That and similarly, the over-etching. The drawbacks of over-etching, that over-etching, if you are over-etching the step, it also needs to be very calibrated. That you should know that what is the etch rate. According to that, I can go for over-etching. If my etch rate is very high, I know that maybe 10 seconds would be more than enough for me for over-etching. If the etch rate is very slow, I can go for 2 minutes maybe. So it depends on what is the etch rate, because if you have not calibrated that and you have over-etched by more time, it can erode your substrate, or even it can damage your mask layer what you are using, maybe photoresist or any other photo mask. So whatever the undesirable etching can occur in that case, because I told you that selectivity is not always infinity ratio 1. It's always maybe 20 ratio 1, maybe 50 ratio 1. So over etching can damage your substrate or the mask films. Okay, so I told you that loading effect is one of the parameters that is also you need to take into account. We did not talk about the loading effect at that time because I knew that in the next slide we'll be talking about. So what is the loading effect? While etching, loading effect, sometimes you say that okay, this is the loading effect. Due to the loading effect, the etch rate changes actually. If generally I would say that I have BHF and that etch rate is 250 angstrom per minute maybe. If it's 250 angstrom, and instead of one wafer, I have 7 wafers loaded in one board and put all together in the same etchant. So in that case, the number of etchants available for the exposed surface area, the number of etchants actually decreases. So this is what we call the loading effect. It may be due to that the number of etchants decrease in that area, that we call it as the etchant limited, as you see in the left figure, or it may be due to that the byproducts that are formed, they are not efficiently removed from there. So if you remember, when even in dry etching, even in wet etching in the lab, we move it a little bit. That movement is actually making it uniform etching, because I want that on the exposed part where actually this film is etched away, that is removed from that part as well. If it's staying there, the etchant would not get into there, and the etch rate would be different at that part if it's in trenches or if it's in small feature sizes. So that's why we always keep moving it a little bit so that the byproducts are removed from that area and fresh etchant comes in contact with the film. Okay, so that we call it as byproduct removal limited. So this is a loading effect. At the same time, if you have some residue left and you go for the over etching process, for very small residue of the film, there are so many large number of etchants available. This situation is also considered as loading effect. So that is imbalance between the two. That is the loading effect. If the exposed area is too much and number of etchants is very small, that we call it as loading effect. Similarly, if in order to remove small residue of film, you have very large number of etchants, that is also loading effect. Okay, microloading, that is locally if you have some material or if you have some pattern that as I told you that if in certain case you have very deep trench or you have very small pattern, in that case it would be very difficult for the etchant to reach and the byproducts to move. So in that case, in that smaller part or the locally in that part of the wafer or the design, we will see that loading effect is occurring. So in order to compensate that, it means, in other words, I am saying that etch rate has changed, the non-uniformity of etch rate has occurred. So in order to compensate that, we will have to go for overetching. Okay. Okay. So micro trenching, that is the formation of small angular notches near the pattern edges. So when you have, in case of high aspect ratio, when you go to etch the deep trenches, you can see that in the corners there are sometimes the notches made. Even maybe in that SCM images you can see it clearly. The first figure and in the third figure you can see that there are trenches in the corners. So those trenches are actually formed due to some optical phenomena that when ions they reflect with the side walls, so there are more probably actually there is more reflection to the corner. So due to that reflection, more ions are actually striking at that corners. So due to that optical effect, actually the scattering effect, those corners are actually etched away more because the ions scattering from the reflecting from the side, they're actually going in that corner. Similarly on the other side walls. So this is one of the effect, and the other effect may be the sheet potential as well, and sometimes it's the mask as well. But these are the two major reasons, that ion reflection from the side walls and mask charging by electrons. So these can create the micro trenches in your pattern. Okay, so now how you actually monitor your process. We know that dry etching, we supply the gases and they react with the surface. So how you can, in the real time, I mean, if I say in situ process, that in situ means that in real time. In real time, how you can monitor that, okay, this is the thickness of the film that has been removed. The total etch rate is actually the removed thickness per second or per minute. And what is the total thickness that has been removed? So we need some monitoring tool, or we need some monitoring equipment that can monitor in situ or in the real time that what is the etch rate. So what we do, that we use OES, that is actually optical emission spectroscopy. What is optical emission spectroscopy? That we may monitor the etchant, or we may monitor the byproducts, or whatever the resultant product is. Both can be used. So initially, you know that when etchant are introduced in the chamber, there would be lot of etchants. Okay, so that etchant, that specific etchant or that specific byproduct has specific functional groups that can be monitored, and each functional group is associated with a certain frequency or certain wavelength, as the graph can show. So for photoresist, the species that can be monitored, it may be the hydrogen or hydroxyl group or carboxyl group. So these are actually having the specific wavelength, and we actually monitor that specific wavelength. The optical emission spectroscopy, that's why the name shows that you monitor the emitted wavelength, that what is the intensity of this wavelength that is emitted. So if I have the etchant, initially the etchant should be having high intensity because they were available so much. After that, when they dissolve when they react with the surface, that should go down. So it means I would say my etch process started. Maybe the next slide will make it clear that the start of the etch is from where the peak goes down. That dark line is actually the etchant, and that dotted line is actually the byproduct or the film product. Okay, so you can see both can be used and both give the same result, that the etchant should go down. At the same time, when etches goes down, it means that byproduct starts. Byproducts, if somebody is monitoring byproducts, he say, oh, etch, it looks like etch process has started because now I can, my optical instrument can measure this wavelength that is actually regarded to that specific byproduct. If some person is monitoring the etchant, he will say that the etchant has gone down, the signal intensity for specific etchant has gone down. It means that the etchants are busy with the film that needs to be removed. After that, the etch process continues, and you can see the very good thing about this process is that you come to know about the endpoint detection, and that is also the monitoring tool named as EDP. That again, when that etchant, if I talk about the etchant, again when it increases, I say that my etchants are, the signal is strong. Now again at this point, the etchant signal is strong, so it means that now it's not, they are not reacting with the substrate because it looks like the substrate has been removed completely. So this is the end stop. Similarly, at that time, byproduct will fall to very low signal value as well. So byproduct again falls to 0. Okay, so this way, by monitoring those specific wavelengths that are actually related to certain etchant or certain byproduct, you can monitor in situ that what is your etched film at this time, how much is left, or whether the endpoint has reached or not reached. So you can use either of these two. So it is named as optical emission spectroscopy. So the name actually tells that optically whatever is emitted, you are actually scoping that, you are actually monitoring that. The emission of those certain wavelengths or certain frequency elements, because those are related to certain functional groups that are coming from the etchant or coming from the byproducts. Okay, so etch equipment, wafer configuration, that table is of interest for you guys, that these days single wafer equipment are actually replacing the batch wafer. I know this thing that the throughput would be high if we are working on a wafer batch instead of a single wafer. As you can see, the throughput, the second line of the table, the throughput is high for the batch processing as compared to the single wafer. But it depends upon that how much time you spend on that wafer, but mostly the throughput would be lower for the single wafer as compared to the batch processing. But all the other parameters, specifically the control and the better calibration, and I would say automation, these are certain parameters that are actually making the people to move towards the single wafer processing. Because in the single wafer, for example, if I say that I am using optical emission spectroscopy, if it's a single wafer, I can exactly find out, okay, this is the endpoint. It will be more accurate, the endpoint, because they are actually the scattered components or wavelengths are actually from a single wafer. But if you have 25 wafers, a batch of wafers, in that case the signal goes up. If I'm talking about the etchant, it goes up, but it won't be that much accurate or that much good control of calibration, because maybe that most of the wafers have been reached their endpoint, but one wafer, due to some non-uniformity, it has not reached. But collectively, the signal will go up. So that's why there is a better control, and we will have more reliable data in that case. As an example, I have taken that the endpoint will be more efficiently detected in single wafer processing as compared to a batch wafer. So due to these benefits of the process characteristics, we are moving towards the single wafer processing as compared to batch wafer. Okay, so low density plasma etchers, because we are not talking about the equipment, so there are different strength of plasma that is used in equipments. It may be low density plasma, it may be medium density plasma, and it may be high density plasma. So one thing you know this thing, that low density plasma or medium density plasma, they are generated by what coupling? Capacitive coupling. Because I told you before that capacitive coupling is used to generate low density plasma. For high density plasma, just like in DRI, we use inductive coupling. Okay, so similarly, it means that depending upon that, actually, you in your equipment, this is one example that coupling means that you are talking about the source of power generation, that whether the power source is capacitively coupled to the electrodes or it's actually inductively coupled to the chamber. So plasma generated by capacitive coupled RF power in this case. Secondly, I know this thing, whenever it's capacitive coupling, the wafer would always be at the cathode, that is the grounded electrode or the negative electrode. So wafer is placed on the negative electrode, and because it's low density plasma, so in that case the energy of the ions, that would be relatively low, but the pressure would be high. So this is typically set up for the low density plasma etchers, the equipment as you can see in the diagram. So in this case, the energy of the plasma, that is low, but the pressure, that is high. It's operated at high pressure, greater than 200 millitorr. So it's actually a trade-off between the energy and the pressure. If it's low energy, you can generate more pressure to actually make it more efficient. So you will see this trade-off in the other equipment as well. Okay, well, medium density plasma etchers. In that case, again, the coupling is done by capacitive coupling, capacitively coupled RF power, and in order to increase the plasma density, we use some magnetic field. As in the figure on the right hand side, you can see that there are the magnet attached, and because it's capacitive coupling, so it would be have positive electrode and negative electrode, and your wafer sits at the negative electrode. The bottom electrode that arrow shows, your wafer actually sits at the bottom electrode or the grounded electrode. So in this case, the energy of the ions, they are relatively higher as compared to the low density, but your pressure goes down. That is the medium pressure in the range of 20 to 200 millitorr. So that trade-off is also seen in this equipment. So that's why I say that it depends that if you're using high density plasma, you operate it at low pressure, and if you're using low density plasma, you operate it at high pressure greater than 200 millitorr. So the last is the high density plasma. In that case, one thing, as I told you, that the high density plasma is generated by the inductive coupling or by the microwave generation or waveguide coupling that we discussed in last time. So capacitive coupling is not used to generate the high density plasma. In this case, the energy of the ions, that would be very high energy, but the plasma pressure, the pressure inside the chamber, that is very low, even less than 15 millitorr. So the same trade-off can be observed here as well. And the diagram on the left hand side shows you that what is how the equipment looks like, that you use the magnetic coil here as well to increase the density, because this is high density. So if you compare it with the previous one, you have small magnet here. Here you have large magnets. And secondly, the coupling method for the power generation is different. Inductive coupling or waveguide coupling, that actually generates the high density plasma. Okay, so actually the etching is completed at this point. So any question about the dry etching before we move to the, because I have 10 extra minutes, so we can discuss about the next topic as well. Any question about the dry etching that she had?
Which is preferred, high density at low pressure or low density at high pressure? What method is preferred?
It depends actually that it depends upon your application, and but mostly whenever you process at high, let's suppose if you have high density plasma, in that case you won't be having very good control over the thickness. If you have very small thickness, it means because etch rate would be high here. So when etch rate is high, you lose the control. Okay, so you lose the control at the same time. In this case, because it's high, very energetic ions, so high energy of the ions, they actually damage your surface as well, the mask or the substrate. So that's why if you want to have very high etch rate, but it's okay for you, if the surface is damaged, you will go with high density plasma. But if I have very thin film that needs to be etched, that's not very high, I don't care with the etch rate. I say okay, the low energy density is fine because I don't want my surface to be damaged, and secondly I want a very good control on the surface.
So it depends on the thickness of the film, not the aspect ratio, right? Like you can have a high aspect ratio, but you could have a very thin film covering it. So if I want to etch that film, then I would go for a low density process than the high density one.
Yes, actually the etch rate, you're talking about the high aspect ratio and?
High aspect ratio and thin thickness. So in that case, I want better control on the etch rate, right? Even though the aspect ratio is high, I would not go for high density plasma because it would damage my, it would over etch.
But actually for the high aspect ratio you need very energetic or more energy to reach that depth.
So I can use a low density plasma with higher pressure, right? It will still give me the same result.
Actually, when you talk about pressure, pressure is, if you remember that pressure is regarding to the number of etchants that are available. So it's the pressure of the gas. It does not, the pressure does not make it directional, or it does not make it energetic. That is regarding towards the plasma or the energy or the ion bombardment. So when you increase the pressure means that the etch rate is more number of etchants are available. But pressure has no effect or has no control on making it directional or making it more energetic. Okay, so because low energy, in the previous cases you see that they are low energy, so in order to have some etch rate, we increase the pressure. So pressure actually increases the etch rate, but it does not make it directional, and for high aspect ratios, we will go for high energies.
So I have a question. In UTA, what kind of plasma etching facility?
That I'm not perfectly sure that what equipment we have. It should be, I'm not very sure that what we have. But we have reactive ion etching, that I know. If we have even deep reactive ion etching in the UT, because I told you that these details, even when you get the training, they don't tell you and you don't need to know. These are details just to have you an understanding of that. While working with that, you just need to know that, okay, this control is, at that time they tell you about this application point of view. They don't train you with the theoretical point of view. You just know that, okay, I need to control the voltage by this knob, and by changing the pressure, for changing the pressure I need to use this knob. So that's what they tell you. What pressure you need to use, why you need to use, that's up to you. The trainers don't tell, and that's why I don't know that what we have in the lab.
Okay, one more question is, when you're explaining cycling etch, can you explain why I'm having some confusion on what is the passivating etching?
Oh, you mean that in the passivation, after the passivation layer, Why we move it from the bottom?
I'm confused. What is the passivating layer?
What is, okay, what material we use, you mean to say?
So why do you passivate?
Oh, why do we passivate? Okay. So actually I told you, in order to have deep, high aspect ratio or deep trenches to pH, let's suppose that I want to achieve this thing. Okay, this is very high aspect ratio. So what I do, that first of all, if this is my substrate, I mask this part. Let's make it a bit thicker. After this is a film that I need to pattern. So what I do, that after masking, I try to etch this thing. Due to the isotropic etching, it will etch like this. If I continue the process, in that case, I'll get something like this. You agree with me? Okay, I don't want like this, I want something like this. I don't want the lateral etching in that case. So what we do in deep reactive ion etching, that there are cycles of passivation layer, deposition and etching process. So you etch, you deposit passivation layer. You etch, you deposit passivation layer. So in that case what happens, that the process is still isotropic. But in the first cycle, I did this thing. After that, I deposit the passivation layer. So that passivation layer, first of all, it deposited. After that passivation layer is deposited, this passivation layer can be moved only from the bottom. Okay. Now when I again go for the next cycle, that is the etching cycle, it will etch sideways as well as downways. So this part, due to the isotropic, this part would be etched this way. But so far as this part is concerned, laterally only that passivation layer is etched. This passivation layer is etched. So that passivation layer has avoided. So this way it continues. So you can see that instead of having something like this, I have achieved something like this. So the passivation layer on the side, in the etching cycle, that sidewall passivation layer is removed, but I have moved deeper. Again the passivation cycle comes, so the sidewalls has still passivation layer, that is removed, but in the same time you move deeper. So this way you keep on moving deeper, deeper and deeper, but you don't move sidewalls. It's only in the first cycle what you move, that's the, in that case you move deeper without moving towards the lateral direction. So that's
How do you decide when to stop?
Sorry?
In the first cycle, how do you decide when to stop? Because that time there's no passivation layer to tell you that.
Yes, that's why I said that you need to multiplex it according to your own process. If I know that, first of all, I should know that how much flexibility I have in the lateral etching process. So if the first cycle is longer, it would be deeper. It means the steps would be deeper, but at the same time I have lost some direction. If I move the steps this much deeper, in that case it would be the lateral would also increase. Got my point? So you are the one who decide that how I need to multiplex. Similarly, if you know what is the etch rate, you should decide that what should be the passivation layer thickness. So for that much time, you actually put the passivation layer on, so that because if the deeper is the thickness, it means that longer is that cycle for the etching, so longer should be the cycle for the deposition. So I mean to say that you may have this thing. If this is a substrate, this is the film. So if the first cycle I make it like this, Okay, or somebody else may make it like this. So you feel the difference. He will find something like this, and you will get something like this. So he is getting his cycles are smaller. He will take more time. He's switching again and again, but he will get more narrow channel.
I have a question. Since we need a deep range like this, I mean that is directional. So why do you choose isotropic etching instead of DRI or RI?
It's not.
We can do, I mean, only RI instead of taking small steps, small isotropic steps, like several times. We can use it. I mean,
Okay.
only DRI.
It's just I'm giving an example. I'm taking it as perfectly isotropic, but you don't have perfectly an isotropic process anywhere. So when I say deep RIE, so it's still RIE, but it has birth cycles. So it means that maybe you go deeper in this way, but at the same time you go lateral this much thickness.
So DRI also has some isotropic etch.
Yes, if you have reactive ion etching, it's not perfectly anisotropic, but it should be close to one that, I mean, the ratio of lateral etch ratio, that should be actually very high. That is, the vertical etch rate would be very high as compared to the lateral etch rate, but it won't be zero actually.
And what about anisotropic etch? I mean, anisotropic wet etch. So, I mean, can you use anisotropic wet etch so that we don't get that isotropic shape?
And that's what I'm saying, that I'm showing it isotropic, but it's not perfectly isotropic. We use, because reactive ion etching is actually an isotropic process. But when I talk about very deep channels, in that case, even in that anisotropic process may look like more isotropic as compared to it should look in less deeper channels.
So that's why we take smaller steps.
Yeah, that's why we take smaller steps, because no process is perfectly anisotropic. It should always have some angle here. Okay, so practically it's not isotropic, but it's you can say that we are actually increasing the anisotropic factor in that by using this cycling. We use the anisotropic process, but we are increasing that by doing that.
So this method can be applied to wet etching process also, right?
Yes, in the wet chemical, you're talking about wet chemical etching?
Yeah, chemicals.
Okay, in the wet chemical etching, I don't know that what passivation layers you'll be using, and after that, how you remove only the passivation layer from the bottom. So usually we don't use that in wet chemical etching. Wet chemical etching is always mostly considered as isotropic. But you know, it's not always isotropic. TMAH, EDP, or some other, they are actually anisotropic processes. You got some question?
Yeah, I mean, like for surface micromachining, for thin film, we use anisotropic wet etch, right? Okay, but for deep array, since we get some isotropic shape, so that's why we take smaller steps.
Yes, and the smaller steps actually help you, as I told you that the smaller the steps, the higher would be the anisotropic. So the smaller the steps, just like I draw that example, that you can increase the steps, but in that case, the anisotropy would be less. You will have more lateral etching as well. Okay, so previously we have discussed about the oxidation. Remember? Oxidation, that is, I told you at that time that to be specifically, we call it as oxidation growth. We call it as the growth of oxidation instead of deposition of oxide layer. So that was the thermal growth of oxidation, or of thermal growth of silicon dioxide. So generally speaking, when we talk about oxidation, we think about thermally grown oxide layer. But it's not always true, because if I want to Do you think that I can grow thermally grown oxide layer on this Hansel? Do you think I can grow oxygen over here? Oh, sorry, silicon dioxide over here? No. Why is it so? Assuming that it's good at that high temperature, it won't melt or somewhere. So why I cannot grow?
It's not made of silicon, so
It's not made of silicon. So you need the silicon substrate to react with steam or to react with oxygen. So it's always, so when we talk about this growth of silicon dioxide, it means we are talking about silicon surface that is having the silicon dioxide on it. If you don't have silicon, you cannot grow silicon dioxide on that. You can deposit silicon dioxide, but you cannot grow it. Okay, so and always keep in mind when you are specifically when if you are appearing in diagnostic or even in the final exam, if Dr. Will sometimes gives some graph or some, so you need to keep these words in mind. If it's written thermally grown, or if it's written thermally deposited, the deposition method. If you remember in the last midterm exam, there was one question: what deposition method gives the best quality oxide? Okay, so because some of you guys were not taking this thing very clearly, I saw some of you wrote it wrong, so I changed it in the class. I said, okay, let's remove the deposition word, because I could see that most of you were doing it wrong. Everybody was saying, okay, this is thermally grown. Some of you got that point that when you are talking about what deposition method, so thermally grown is not the deposition method. Okay, so this is what I'm saying, that at that time I changed it because I know you have not studied the CVD process. So I changed it and I checked it according to that key. But maybe in final exam, Dr. Iqbal will assume that you should know if he's talking about the deposition method, you will exclude that thermally grown method.
So what method does give the best oxide?
In the deposition method or
Yes.
generally?
Generally and in the deposition method.
And generally, I would say that we consider always the thermally grown oxide, that is actually a native oxide. If we talk about that at room temperature, the thermally grown oxide at room temperature, that is actually the best oxide layer. That it actually grows.
How about deposition?
In the deposition, there is actually plasma enhanced deposition, that PECVD, and there is actually
What's the best one?
the best one is that is done at low pressure. Plasma enhanced is not good quality. So low pressure LPCVD.
LPCVD is the best one.
LPCVD is better. If we talk about PECVD and LPCVD,